Okay, YouTube, in this video I'm going to introduce the concept of a parametric equation a little informally, and then I'm going to define it formally up here. But let's go ahead and start with what parametric equations are, and then I'll finish this video by kind of sketching what a plane curve C would look like if I gave you a parametric equation definition for some rectangular equation. So let's go ahead and start with parametric equation. First things first, the root of parametric is parameter. And a parameter is like a guideline that you have to follow here. And when we discuss parameters in math, a lot of the time, I'm not going to say it's all the time, but we discuss time a lot of the time. And so what we want to do is describe, say, maybe the motion of a particle or some mass through this, space. But what we know is, at least if we were to say, like, this is some particle moving through space here in this diagram, you can see that there are arrows indicating that it started here and moved through this path. We would say that at first, at the very least, we could say that there's some vector that described its motion here. And we could actually classify this if we knew its magnitude and direction. But what I would have everybody notice is that it has an x component and it has a y component. So in other words, you could see that it was fired a little faster or harder, or whatever you want to say, in an upward direction than it was in a sideward direction. But maybe our goal is not to describe, its motion so much, but its motion with respect to time. So what we would say is, well, as time is flowing, it's moving in an x direction at this kind of speed, and as time is flowing also, it's moving in a y direction at this speed. So we could start to comment on things like how fast is it going in a y direction or upward, or how fast is it going in an x direction or horizontally with respect to our frame of reference here, but with respect to time. Okay, so what we want to do is a lot of the times describe how it's moving in different directions, x and y, but with respect to a given amount of time that's passed already. So let's go ahead and say, now that that's the case, I kind of understand that it's moving differently in an x direction, than it is in its motion in a y direction. We could define them both as a function of time. We say f and g are continuous functions of t. T is going to be what we call our parameter. Okay, just get used to the fact that we use t. It's not always going to represent time, but we just often use t for time. So we use t all together. So we say, all right, f and g are continuous functions of, say, time on some interval I. It says the set of ordered pairs. So now notice what this is we're defining a point in space. So this describes like our particle. Maybe this is our particle here. But we say, here is its x-word direction function as a function of time, and here's its y-word direction as a function of time. And what they do is they kind of, if they were to trace out a path, they sweep out this what we call plane curve C. So this is our curve, and we call this curve C. But the equations x equals f of t and y equals g of t are our parametric equations for C, and we say that t is the parameter. So what you're seeing here, at least in this plane curve that I was kind of drawing on here, we could see that there's some rectangular equation. This is how we would normally interpret a graph. It looks like we have a second-degree polynomial equation. It's got a negative leading coefficient, so it's going to open downward. It's got a y or x-axis reflection, and it's really kind of wide. It looks like 1/72 is our a value. So, anyways, here's this, and you can see that we're labeling points on this graph. We say at time 0, then it would have been at this point right here. What we're doing is we're actually just going to take this rectangular equation and say, well, now actually we could describe it by saying any point on this curve. This is right 0, 0, right? Okay. What we're really saying is any point x, y on the curve now actually is going to follow this pattern. The x value is going to be equal to 24 times the square root of 2 times whatever the time is, and we're saying, I guess, in like units of time. I would say maybe seconds here is a normal unit of time. And we're saying, but the y direction, y is equal to negative 16 times squared plus 24 root 2 times the time. So the idea here is that we have different behaviors in different directions, okay? And every point on the outside of this is equal to this. So if I wanted to say, they were able to determine here, and we could certainly do this as well, but the time at which it's at its apex, at the highest point here, was 3 times the square root of 2 divided by 4. We could say we could evaluate this actually. 2, the root of that times 3 equals divided by 4, and about 1.06 seconds. We could actually say, plug that into this equation right here, and what we're going to find out are the coordinates of its vertex, and actually, we could check this out, but it's actually at 3618. And you would get the same thing as if you plugged in this exact value in for time here and here. So here's what we want to do. We want to say, moving forward, we're going to take rectangular equations, which we'll practice putting into parametric form later, but for right now, saying we could define them parametrically, or at least based on some parameter time, and say that they behave differently in different directions, but every point that we find here is going to be just a series of x's and y's that we have to evaluate for. So this parametric equation up here, it says sketch a plane curve, x is equal to t squared minus 4 and y is equal to t over 2, where t is some number between -2 and +3 and including those. So the first thing we always want to do is this. We're going to come up with the table of values. As a matter of fact, we're going to say x and y. The thing here is this, we just have to remember that x is following one formula or function and y is following a different function of time. So when we plug these in, I'm going to make a suggestion here. Let's go through the whole, at least, domain of values that we plugged into this here. So -2 up to 3 is kind of like the domain in terms of time, with respect to time, okay? Not with respect to x and y. But we say here are, input values for our, say, x here. Actually, silly. We have to build in one more column. We have our x and our y. This is our time column. Sorry, I kind of assumed that people, made a mistake there. We say 0, 1, 2, 3. Okay. Let's try this again. Now that we have our time parameter in here, we're going to say what are our x values, what are our y values? And we say, well, if x is obeying this rule, t squared minus 4, I always recommend going through and just find all the x's first since it's the same rule, and then go find all the y's that pair with them. So if we're going to go through t squared minus 4, if I said -2 squared before minus 4 is 0, and I would say, okay, well, t squared minus 4, if I plugged in -1, I get 1 minus 4 is -3. If I plugged in 0, I get -4. If I plugged in 1, I get 1 squared minus 4 is -3 again. And then we would say 2 squared minus 4 would be 0 again. And then we say 3 squared minus 4 is 9 minus 4 is 5. Okay, so now we're going to run through our y values. And these are all just cut these values in half. So we'd say -2 over 2 is -1. We put a -1 over 2, we get -1/2. 0 over 2 is 0, of course. And then 1 over 2 is 1/2. If we put 2 over 2 is 1. And then 3 over 2, we'll call it 3/2 or 1.5. So what we're going to do now is we're going to go through and we're going to plot all of these different points. Now, I'll tell you what, where you are used to probably labeling these with some XY pair when you draw them, what we're going to be doing is labeling them with times. We're going to say at this time it was here, at this time it was here, at this time it was here, or whatever the parameter is. At this parameter point, it was there in terms of x and y. So we say starting at 0, -1, we're just going to put a point here. And, in terms of a particle motion, this is very appropriate. You'll see this on a graph a lot of the time. We say, here you go. This is where it was initially. So now it moves to -3, -1/2. Now, -3 is this way, 3, and then down 1/2 would be right here. So again, I'm not going to label this with the XY pair. What I am going to do is I'm going to connect these, and I'm going to put a little arrow right here. And I'm going to say this is time is 1. Now, I don't have to put the arrow if I label times, but I'm doing both on this one. In this video, we say -4 zeros here. I just want to really emphasize that you could do either one. We say this is time 3, and then we say -3, 1/2 would be here. So we say time 4. This was where it was, 4 units in. Here's my arrow, and then we would say, okay, so 0, 1, 0, 1. Whoops, that was -3/2. I went up too far. We say -3/2. Kind of got it up there. There we go. This is time 4. 0, 1. So we're going to come over here. We'll draw our arrow. This is time 5. Actually, technically, let me go back and say that this is supposed to be -2. This is -1. This is 0, 1, and 2. I was counting stops there, pardon me. And then we say, okay, so 5, 3/2. So we'd say 5 would be right 5, and then up 1/2 would be here. So this is our 5th stop. But this is at time equals 3, +3 units of time. We could say -2 you could represent as 2 seconds before what you might consider an initial frame of reference, okay? So we say here's the path of this object over time. You can see it's kind of a sideways parabola, okay? But when you graph things in parametric form, you're going to plug in different values of t for x and y, and then go plug in all those points. And you have to indicate what we call the orientation of the curve. So you need arrows, or you can label times. In the next video, we'll talk about how you eliminate the parameter and go from parametric form, these, back to an original rectangular equation that you probably used to. Cheers.